3 in the morning, Red Bull number 4, and I'm staring at a stack trace that makes absolutely no sense. The frame is rendering, but the console's throwing CORS errors that shouldn't exist because I've disabled every security header imaginable. And then it hits me, the execution context is wrong. The Sandbox isn't just running the code, it's running it in the parent Windows context. 47 hours into this build, that single realization changed everything. Today I'm going to show you exactly how I built a working clone of Claude's artifacts feature, the thing that lets you write code and see it render in real time right next to the chat. Not a toy demo, not a conceptual overview, the actual production system. We're talking sandboxed execution, real-time streaming, security isolation, the works. By the end of this, you'll have the complete codebase and understand every architectural decision. Let's get into it. So why build this at all? Because understanding how these systems work makes you a better engineer, and honestly, the existing tutorials on this topic are surface-level garbage. They show you in a frame with circdoc and call a day. That's not an artifact system. That's a security vulnerability with syntax highlighting. Here's the stack I landed on after trying 3 different approaches. The front end is Next.js 14 with the App Router. And before you ask, yes, I tried Remix. The streaming primitives in Next are just better for this use case. The execution environment is a custom WebContainer-inspired sandbox running in a dedicated web worker with a message-passing API. The AI layer is Claude 3.5 Sonnet through Anthropic's streaming API, and the whole thing deploys to versatile edge functions with some clever tricks to handle the long-running connections. Why this exact combination? The worker-based sandbox gives us true isolation without the latency penalty of server-side execution. Edge functions let stream the AI response while processing it incrementally. And Next.js server components handle the initial render fast enough that the perceived latency is almost zero. But here's what nobody tells you about this architecture. The hard part isn't any individual piece, it's the orchestration between them. You've got 3 async streams that need to coordinate: the AI output, the code extraction, and the sandbox execution. Get the timing wrong, and you get flickering, race conditions, or worse, code executing out of order. Let's start with the sandbox, because it's the foundation everything else builds on. The naive approach is to use a frame with the sandbox attribute and inject code via circdoc. This works for static HTML, but falls apart the moment you need JavaScript execution with any real capability. The sandbox attribute is too restrictive for useful code and too permissive for untrusted code simultaneously. Here's what I built instead: a dedicated web worker that acts as a process manager for isolated execution contexts. The worker maintains its own virtual file system in memory, intercepts all network requests through a custom fetch shim, and exposes a controlled set of browser APIs through a proxy layer. The actual code execution happens inside a with statement that shadows dangerous globals. Yes, with statements. I know, we all learn they're evil. But for sandboxing, they're actually perfect because they let you intercept property access at the scope level. The worker receives code chunks via post message, writes them to the virtual file system, resolve imports against a curated package registry, and then evaluates the bundle in the isolated context. All console outputs, errors, and DOM mutations get serialized and sent back to the main thread. The critical insight here is that you're not trying to make arbitrary code safe. You're creating a constrained environment where the code can do useful things without dangerous things even being possible. Block the prototype chain modifications, shadow eval and function, intercept dynamic imports, and you've eliminated 90% of the attack surface. Now, if you've looked into this space at all, you've probably heard of WebContainers, the tech stack Blitz uses for their in-browser node environments. They took a different approach: full node compatibility in the browser via WebAssembly. It's incredibly impressive engineering, but it comes with trade-offs. Cold start time is measured in seconds. Memory usage is substantial, and you need to download several megabytes before anything runs. For an artifact system where you're executing small code snippets dozens of times per session, that overhead kills the experience. My approach sacrifices node compatibility for speed. I'm targeting browser-native JavaScript plus React and a curated set of packages that are pre-bundled and cached. The execution startup is under 50 milliseconds. Memory footprint stays under 20 megs per session, and there's no cold start penalty after the worker initializes. But here's where it gets interesting, and this is something I haven't seen documented anywhere. You can actually hybrid these approaches. Use the lightweight sandbox for the common case of React components and simple scripts, but fall back to a web container-style environment for complex node-specific code. The trick is detecting which path you need during the code analysis phase before execution. I implemented a heuristic that examines imports and API usage. If it's all browser-compatible, fast path. If it needs node built-ins like FS or path, slow path with full emulation. In practice, about 95% of generated artifacts hit the fast path. This is where the AI integration gets genuinely tricky. Claude's streaming API sends you tokens one at a time, but you can't execute partial code. You need complete, parsable chunks. The naive solution is to wait for the full response, extract code blocks, then execute. But that defeats the entire purpose of streaming. Users want to see results building up in real time. Here's the algorithm I developed. As tokens arrive, I maintain a running parser state that tracks whether we're inside a code block, what language it is, and the current nesting depth of braces and brackets. When the parser detects a complete statement or expression, it emits that chunk to the sandbox immediately. For React components, a complete chunk is either a full function component definition, a hook call, or a JSX element. The parser doesn't need to understand JavaScript semantics fully. It just needs to track balance delimiters and recognize common patterns. But incomplete chunks will absolutely break your sandbox if you send them. So the parser maintains a buffer and only flushes when it's confident the code is syntactically valid. The error boundary implementation is equally critical. When stream code fails, and it will fail, Claude makes syntax errors too. You need to isolate that failure without killing the entire execution context. Each chunk executes in a try-catch that reports errors back to the UI without halting the stream. The UI shows the error inline while continuing to receive and attempt subsequent chunks. Sometimes a later chunk fixes an earlier error, and the user sees the component suddenly start working. It's actually a pretty satisfying experience. Here's the part that took me from a working prototype to something actually useful, the prompts. And I'm going to share the exact system prompt because I think this is where most tutorials fail you. They hand-wave past the AI integration like it's trivial. It's not. The system prompt needs to accomplish 4 things simultaneously. First, it needs to establish the output format. Code must be in specific markdown blocks with language tags. Second, it needs to constrain the code style to patterns the sandbox handles well. Third, it needs to front-load the component structure so streaming works correctly. Fourth, it needs to handle the conversational context for iterative refinement. The key breakthrough was instruction ordering. I discovered through testing that Claude weighs earlier system prompt content more heavily when under token pressure. So the format requirements come first, then the sandbox constraints, then the style guidelines. The actual prompt is about 800 tokens, which feels long until you realize it's preventing thousands of failed executions. The other non-obvious learning. Few-shot examples in the system prompt dramatically improve output consistency. I include 3 canonical examples covering a simple component, a component with hooks, and a component with external data. Claude pattern matches against these and produces code that's structurally similar, which means my parser's heuristics hit more often. All right, we've got code executing in a sandbox. Now we need to make it actually production ready, which means security hardening, rate limiting, and handling the edge cases that will absolutely happen when real users show up. Security first. The sandbox isolation is good, but it's defense in depth, not the only defense. I implemented CSP headers that prevent any artifact from loading external resources except from a allow-listed CDN set. The iframe uses the sandbox attribute, even though the worker provides isolation, belt, and suspenders. All post-message communication uses structured clone algorithm serialization, which prevents prototype pollution attacks. Rate limiting is more nuanced than you'd think. You're not just rate limiting API calls, you're rate limiting execution cycles in the sandbox. A malicious or buggy artifact could spin an infinite loop, exhausting the worker. So I implemented an execution budget. Each artifact gets 10,000 operations maximum, tracked via an instrumentation pass during parsing that injects counter increments. Hit the budget and execution terminates cleanly. The edge cases that bit me hardest. Artifacts that leak memory through retained closures, artifacts that register event listeners that persist across executions, artifacts that mutate global state the parser doesn't catch. Each of these required specific handling. The closure leaks are caught by fully destroying and recreating the execution context every 10 runs. Event listeners are handled by the proxy layer that tracks all registrations and bulk removes them on context reset. Global state mutation. Honestly, I just block assignment to window properties entirely. Final stretch. The deployment pipeline here is doing something slightly unusual, and I want to explain why. The edge function that handles the AI streaming has a maximum duration of 30 seconds on Versal's hobby plan. Extended conversations can easily exceed that. My solution is response chunking with continuation tokens. When the function approaches its timeout, it gracefully closes the stream and includes a continuation token in the final chunk. The client detects this, automatically reconnects with the token, and the conversation resumes seamlessly. Users don't even notice. Performance optimization worth calling out. The Sandbox worker and its dependencies get bundled into a single file that's cached aggressively. First visit downloads about 140 kilobytes. Subsequent visits hit the cache, and the worker initializes from memory in under 20 milliseconds. The artifact preview uses React 18's concurrent features for rendering, so even complex components mounting doesn't block the main thread. If I were starting over tomorrow, here's what I'd do differently. First, I'd build the streaming parser as a proper state machine from day one instead of the regex-based hack I started with. Second, I'd implement virtual file system persistence earlier. Users want to reference previous artifacts, and I had to retrofit that feature. Third, I'd add collaborative editing from the start because the architecture changes required for real-time sync are invasive. The complete codebase is linked in the description. MIT licensed, fork it, and build something. If this was useful, I'm going deep on browser-based AI architecture for the next few months. Subscribe if that's your thing. I'll see you in the next one.